Welcome back to Probability and Statistics 1. This is Unit 3, in which we're discussing some of the fundamental concepts of probability theory in the context of discrete probability spaces. And in this set of slides, we're going to introduce the very important concept of expected value. The expected value of a random variable is essentially its average value. If you could imagine observing it many, many times under the same conditions and just computing the average of what the random variable turns up as, that would be ideally what the expected value is. To kind of dig a little deeper in it, let's consider an example. Suppose you're considering an investment. There's quite a bit of risk, though. If you invest, there's a 1 in 2 chance that you'll actually lose your money. So a 50% chance that you'll lose your money. And even if you don't lose your money, there's still a 1 in 3 chance that you'll only break even. But there is a 1 in 6 chance that you'll actually quadruple your principal. So should you make this investment? Well, it seems like the key question we ought to ask in this situation is, what rate of return could we expect on average from an investment like this? And so let's think about that for a second. Here, I'm going to think about the rate of the return as the amount of money you get from the investment in addition to your principal. So if you lose everything, right, your rate of return is actually -1. You lost your principal. If you break even, your rate of return is 0, right? You didn't lose your principal, but you didn't make any money. And then if you quadruple your principal, your rate of return is actually 3, right, or 300%, because like if you had invested $100, then you got $300, you got that back, and in addition, you got $300, and so that additional money would be what we're talking about when we talk about the rate of return being 3. So those are the three cases for the rate of return. You get a rate of return of -1 with probability a half, 0 with probability a third, and 3 with probability a sixth. So should we make the investment? Well, just imagine what would happen if, say, 1,000,000 people independently made this kind of investment. What would you expect? You would expect half of them to lose their money, a third of them to break even, and a sixth of them to quadruple their money. So what would be the average rate of return among these million investors? Well, it'd be half of a million who, right, got a rate of return of -1, a third of a million who got a rate of return of 0, and a sixth of a million who got a rate of return of 3, and then of course divided by a million. And the 10 to the 6 cancel out there, and what you get is 1/2 times -1 plus 1/3 times 0 plus 1/6 times 3. And that turns out to be 0. So on average, individuals would make 0 from this investment. So it's not really an opportunity, a very good opportunity if your goal is to make money, right? On average, you would not do that. You wouldn't lose money, but you wouldn't make any money either. What we want to get out of this example is this idea of computing expected value by taking the value of a random variable, like R here, multiplying it by its probability, and then summing that over all possible values. That's what's happening, right? When we look at that 1/2 times -1, 1/2 is the probability of -1, so we look at that product. 1/3 is the probability of 0, so we have 1/3 times 0, and then 1/6 is the probability of 3, so we have 1/6 times 3. Add those up, that gets the expected value. And that motivates our definition of expected value here. Let x be a discrete, real-valued random variable whose possible values form the set S sub x. The expected value of x is denoted by the symbol E of x and is defined by the expected value of x is the sum over all possible values of x of the quantity x times the probability that the random variable equals x. And you could just express that as the sum over all possible values of x times the probability mass function of x. The expected value of a random variable is another word for its mean or its average, and sometimes we're going to denote it sort of in using the statistical notation by mu or mu sub x if we need to emphasize that this is the mean of x. But the key thing to get from the definition is, again, just like the example, to find expected value, look at possible values, multiply each by its corresponding probability, and then sum. So here's a few discussion questions looking for the expected value of the sum of a pair of dice, looking at the expected number of red balls in a random sample from an urn, and looking at the expected value of an indicator function. If you look at that third bullet, x there is called the indicator function of e because x is equal to 1 if the event e occurs and 0 otherwise. And so see if you can apply the definition of expected value to each of those cases and find the expected value. We'll discuss that further in class. Here's another way to think about expected value. And I want to show this through an example, but it's generally applicable. Let's toss a fair coin 3 times and let x be the number of heads that we obtain. We've already seen that the distribution of x is given here. The possible values are the integers from 0 to 3, and there you see the probabilities, 1/8, 3/8, 3/8, and 1/8. So the expected value of x would be just the sum of those column products, right? 0 times an eighth plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8. And that turns out to be 1.5. And that kind of makes sense. If it's a fair coin, it's going to be heads on average half the time. If you toss it 3 times, half of that would be 1.5, right? So that seems to make sense. But let's look at it another way. Because remember, that random variable x really comes from the experiment of tossing 3 coins and just recording the outcomes, right? We could do a lot of things with that. We could measure the number of heads, we could measure the number of tails, and so on. But look at that larger sample space of the experiment of just tossing a coin 3 times. So there you see the expression of that. There's 8 possible outcomes, right? And you see them listed from head, all the way to tail, tail, tail. And then for each outcome, there's a value of x associated with that. X is the number of heads, so there you see it. And of course, this is a fair coin, so all those outcomes are equally likely. The point I want to make with this is that this idea of multiplying the value of a random variable by the probability plays out in this context as well. If I multiply each row here, right? So if I take the product of the value of x times the value of the mass function, I get 3 times an eighth for the first outcome, head. 2 times an eighth for the second one, right? Because it's HHT, 2 heads, and so on. Now that last column is kind of like the definition of expected value, except we're doing it in the sample space for tossing a 3 coin. We're not doing it over the possible values of x, right? But in a way we are, because if you look at the numbers there in that right-hand column, you'll see the terms back on the previous slide. These terms 0 times an eighth plus 1 times 3/8 plus 2 times 3/8 and so on. You'll see them here, right? There's 0 times an eighth. 1 times 3/8 is related to those 3 elements of the sample space, right, of the larger experiment, right, because they are the 3 outcomes which give us an x value of 1. So you get that 1 times 3/8 there. The 2 times 3/8 comes from the 3 outcomes which have an x value of 2. And then the 3 times 1/8 comes from the outcome that has an x value of 3. And all those together exhaust the sample space. So if I sum up the numbers in the right-hand column of my table, I get 1.5, and of course that's going to be exactly the same as the definition of expected value. And what this shows is that there's an alternative formula for the expected value. Instead of summing over possible values of x, the random variable, which is what the definition does, you can go back to the sample space that x is defined on and sum the values of x over all those possible outcomes times the probability of each outcome. And that'll give you exactly the same number. And so that's theorem 3.3. If x is a real valued random variable defined on a discrete probability space S with probability mass function P, then the expected value of x is the sum over all outcomes in S of the value of x at S times the probability mass function at S. And this, of course, is where we are using the fact that x is a function defined on the sample space. And I'm actually, including that in the notation here because that's essential. There's a second property of expected value that's proven in much the same way. I'm going to omit the proof here, but it's kind of the same sort of thing. It has to do with computing the expected value of a function of a random variable. So like, what's the expected value of x squared? Well, the theorem 3.4 addresses this. It looks at the expected value of any function f of a random variable x. And a simple formula for that is you simply sum over all possible values of x the value of f of x times the probability that x equals little x. And that'll give you the expected value of f of x. And as I said, the proof of that is very similar to the proof of the theorem 3.3, or the idea that we saw about theorem 3.3. And then as a corollary to 3.4, if you combine 3.4 and 3.3, you get corollary 3.5, which shows you how to compute the expected value of a function of a random variable by going back to the probability space that x is defined on. And again, it's values of f of x times the probability of those values. So let's look at some examples. Let x have a discrete uniform distributions on the integers from 0 to 5. Let's find the expected value of x squared, and then let's find the expected value of x minus a, the quantity squared, where a can be any constant. So since we have the discrete uniform distribution, all the outcomes from 0 to 5 are equally likely. There are 6 outcomes, and so the probability of each is 1/6. So the expected value of x squared would be sum over all possible values of x, that is from 0 to 5, x squared times the probability mass function at x. And that's, of course, 1/6. So we just get 1/6 times the sum of x squared, and that turns out to be 55/6, or 9 1/6. The second question was a little bit interesting because we don't have a value for a. But that really doesn't matter in terms of expected values. To find the expected value of x minus a, the quantity squared, it's just values of x minus a squared. You look at all possible values of x minus a squared, and you multiply each by the probability that it occurs. And that's 1/6. So we have the sum from x equals 0 to 5 of 1/6. And you can see me just working that out here in the slides. And we get, finally, as an answer, 55/6 minus 5 times a plus a squared. And so it makes sense that the expected value of x minus a, the quantity squared, would depend on a, right? And so that's why we get a function of a out of that expected value. And so that's just summarizing that result. And then this is something you really should look at. In this particular example, we've got a quadratic in a, right, as our expected value, and it opens upward, so it'll have a minimum value. I suggest that you find the value of a that minimizes that expected value, and then compare that to the expected value of x itself, right? X has the discrete uniform distribution on 0 to 5, so you can compute that pretty easily, and see what you get from those two questions. Theorem 3.6 lists some of the very basic properties of expected value. First of all, the expected value of a sum of two random variables is the sum of the expected values. That's actually very easy to prove, not from the definition of expected value, but from theorem 3.3. Because the expected value of x plus y would just be the sum over all s in the sample space of x sub s plus y sub s all times p of s. And that would break up into two sums and give us that first bullet point. So the expected value of x plus y is the expected value of x plus the expected value of y. The expected value of a constant times any random variable, the constant just pops out. And you can see that from any of the formulas we have for expected value. That constant will be inside the sum, and since it's a constant, it'll just pop out. So those first two bullet points there say together that expected value is linear, right? If you have a linear combination of expected values, then the expected value of that is the linear combination of the expected values. The third bullet point may look a little strange, but it's saying something very simple. It says that if x, a random variable x, is actually a constant, right? So that would mean that it equals some value, which I'm calling c here, with probability 1, then the expected value of x is just also equal to c. So if x is always 5, then the expected value of x is 5. Another way of saying this is that the expected value of 5 is 5. The fourth bullet is saying something similar but a little more general. If x is always greater than or equal to some value, then the expected value will also be greater than or equal to that value. So if x is always greater than or equal to 5, then the average value of x will be greater than or equal to 5. And again, this is easy to prove from the definition. And then the last bullet is the triangle inequality. It says that the absolute value of the expected value of a sum is less than or equal to the absolute value of the expected value of the first guy plus the absolute value of the expected value of the second. And this is useful in a lot of theoretical settings. It's an important property that I wanted to go ahead and get out there. And basically, it's not hard to prove either, just from the fact that the triangle inequality applies to real numbers too. Let's do another example. Let's toss a fair coin 3 times and let x be the number of heads obtained. And let's compute the expected value of x minus 1.5. We basically already computed the expected value of x minus a in our previous example, so I could just plug in a equal 1.5 and do that here. But let me show you how to use the theorem, because it's in some sense easier. So if you expand x minus 1.5 squared, you would get x squared minus 3x plus 2.25. Now that you can break up, because it's a sum of 3 terms, the expected value you could break up into a sum of 3 expected values. Expected value of x squared, and then minus 3 times the expected value of x, and there I've pulled the 3 out of the expected value as well, right? And then plus the expected value of 2.25. And then each of these can be computed by using the fact that we know the distribution of x. So we've already seen that the expected value of x itself is 1.5. There you see the expected value of x squared. That would just be possible values of x squared, right? 0 squared times their corresponding probabilities. So you get 0 squared times an eighth, 1 squared times 3/8, and so on. That's 3. Expected value of 2.25 is, of course, just 2.25. And so then putting all that together, which we're doing here, gives us the final answer of 0.75. The expected value of x minus 1.5, the quantity squared, is 0.75. And here's some discussion questions that you can solve using the ideas we've discussed here. We'll talk about these more in class. I would point out that the second guy is kind of interesting, but we're trying to find the expected value of e to the t times r, where t is an arbitrary real number. So this goes very much in line with the example we did earlier about expected value of x minus a. You treat it in exactly the same way. Third bullet point asks an interesting question. Does every random variable actually have an expected value? If so, prove it. If not, give an example. Okay, we'll stop here for now. Next up is the concept of variance and standard deviation, which you may remember from statistics. That actually is just kind of a little add-on to the concept of expected value. We'll define variance and standard deviation in terms of expected value. and we'll see that all the properties that we know of expected value can help us in computing variance. So that's for next time. In the meantime, y'all take care. We'll talk to you soon.